Work is a thermodynamic process in which the system interacts with its surroundings and exchanges energy. When a force acts on the system, the result is work. To define a process as work, the force needs to act on the system boundary, and the boundary must move. For example, a piston cylinder contains water that is heated until it is vaporized. The pressure increase will cause the piston to move, which results in work. Notice that if the piston cylinder was placed in a vacuum, the expansion of the piston cylinder would not be considered work since there is no opposing force to counteract the displacement. We usually consider work to be positive when it is done by the system and negative when it is done to the system. For example, by compressing a gas inside a piston cylinder, we exert negative work. If we let the gas expand, pushing against the weight of the piston, positive work is exerted. We represent work as the area underneath the curve in a PV diagram. There are several ways that we can take to go from an initial to a final state. This is called the process path. Depending on the process path, the area under the curve will differ, meaning that work is path dependent. Moving boundary work is defined as the expansion or compression work done to or by a system. In reality, it is impossible to measure the exact moving boundary work because the process occurs very fast. Therefore, we assume a quasi-equilibrium process, meaning that the work output is maximum and work input is minimum. The actual boundary work is smaller than the quasi-equilibrium work. To find the total boundary work, we calculate the integral of the pressure multiplied by the rate of change of the volume. For constant volume processes, the area under the curve on the PV diagram is 0. Therefore, the work is also 0. For constant pressure processes, we consider P as a constant and we integrate with respect to the volume. We find that the boundary work for this type of process is equal to the pressure multiplied by the change in volume. For constant temperature processes, we use the ideal gas equation to replace P with mass times R times temperature divided by volume. We consider M, R, and T to be constants, and we integrate with respect to the volume. We find that the boundary work is equal to mRT multiplied by ln of V2 divided by V1. For polytropic processes, the pressure and volume vary according to the relationship P V to the n equals some constant C. We can use this relationship to replace P by C V to the minus n. Again, we integrate with respect to the volume, and we obtain the following equation. We can replace C to obtain an equation with the initial and final pressure. Electrical work is caused by electrons crossing the system boundary. Electrical work is equal to the integral of the voltage multiplied by the current with respect to the time elapsed. Since the voltage and the current are constants, we can take them out of the integral and integrate with respect to time. Shaft work corresponds to the energy transmission when a rotating shaft is involved. Shaft work is equal to the force multiplied by the distance it is applied. The force is equal to the torque divided by the radius of the shaft, and the distance is equal to the circumference of the shaft multiplied by the number of revolutions. Therefore, the shaft work can be defined by this equation. Finally, spring work occurs when a force is applied to a spring, changing its length. The spring work is equal to the integral of the force with respect to the length x. Since the force applied to a spring is proportional to its spring constant multiplied by its length, we can obtain the following integral. Integrating with respect to x, we find that the spring work is equal to this equation.